Okay, so we're talking about 11.1, and then temperature as a fundamental dimension. As a fundamental dimension. Okay, so can anybody tell me what temperature is? What are you measuring there in temperature? What exactly is it that you're measuring? What is temperature?
It's isn't it the measure of molecular activity?
Yes, measure of molecular activity. So the higher the temperature, we're gonna have more or less molecular activity.
The more.
More, okay. So what is molecular activity? What does it actually mean?
How fast the molecules are moving.
Yeah, they're moving, right? So what happens in so that works in a gas, right? What about in a solid? Do the molecules actually move around?
Well, don't they vibrate in place?
Oh, they vibrate, right? So important thing here, they vibrate, right? So they vibrate. Now that we're going to sit there and they're going to vibrate like so as they vibrate. So the more temperature you put, or the higher the temperature gets, the more they're going to vibrate, right? So the lesser the temperature, the less they're going to vibrate, right? So can somebody tie this to me with absolute zero? What does absolute zero mean?
Like Kelvin zero, where there's no heat whatsoever, nothing
Okay,
moves.
absolute zero is when you're 0 degree Kelvin, right? You're 0 degree Kelvin, and that means that you have absolutely no vibration. The molecules are at a standstill. They just sit there without vibrating, right? In other words, there is nothing in there, okay? So good. So that's a good thing to tie in there with absolute zero, okay? All right. Okay, so what are the 4 different types of measurements that we have that are commonly used to measure temperature? You know these 4, right? You have Celsius, Fahrenheit, Rankine, and you have Kelvin. And so these 2 are tied together, and these 2 are tied together, right? So Kelvin is from Celsius. Now, what do you have to do to get Kelvin? You have 270. Right. Rankine. What do you add here?
459.
459. I always
Yeah.
forget this. It's 459 and 456. 459, is it? Yes, it is 459. Okay, 459. Okay, so you've been drilled into these to converting Celsius to Fahrenheit. So I'm not going to go to, well, okay, let's do this. So we have Fahrenheit minus 32, right? 5/9 is Celsius, right? Okay. So we got this guy. So you know this guy. So you know different. You know how to translate between the two. What is this 32? What is the significance of the 32? Anybody?
Water freezes at Fahrenheit 32.
Fahrenheit, right?
Zero.
Yeah, good. So this is the freezing point of water. Okay. All right. 5/9 is the ratio between in Celsius. You have 100 degrees between melting and boiling, whereas in Fahrenheit you have 180, right? So this is basically 100 over 180, which is 5/9, right? That's where that 5/9 comes from. Okay, so should be all review for you. let's kind of take a look at the ideal gas law. All right, the gas law that we were talking about earlier. PV is equal to MRT. Okay, PV is equal to MRT. Depending on your reader, sometimes it'll say PV equals nRT. Okay, your book prefers PV equals MRT. Okay, where M is the mass, R is the ideal gas constant, pressure, volume, and temperature, right? So this is on page 359. Let's see. Okay, what do we need to learn here? What does the book actually want us to do? Okay, T is going to be an absolute temperature. So it's going to be Kelvin, okay, or Rankine, whichever one you're using. Okay, so flip the page and we go over there. We have a figure there. Well, what do we got? No, not that. So let's proceed to run a series of experiments, starting with the surrounding temperature equal to the T reference. And a long time, so we're gonna have T. So let's just go and say we have a one state. At one state, we're gonna have P1, V1, and T1, okay? The mass is gonna stay the same. This is just a constant, so this stays the same. So let's go ahead and compare this in the second state. So you either raise the temperature, lower the temperature, whatever you did, right? Okay, so what we want to know is what is going to happen here, okay? So if we say that the volume stays the same, okay, in other words, V1 and V2 are the same, let's go ahead, we're trying to find the relationship between P1, P2, T1, and T2, okay? Your book goes around doing it in one way. The easy way is just go ahead and divide both sides here, right? This guy goes away. We said that this guy was going to stay the same. So P1 over P2 is equal to T1 over T2. Okay. So that's the type of relationship you're going to have. And if you wanted to solve the second pressure, if you're given these three, you can go ahead and find that out. Okay. So that's pretty simple. And then we have that. Let's go ahead and do example 11.1. Now we should have two of them. Let's do 11.2. Let's do 11.2. Okay, let's do 11.2. See what we can find. Okay, so example 11.2. We have on a summer day in Phoenix, the inside room temperature is maintained at 68 while the outdoor temperature is 110. What is the outdoor indoor temperature difference in degrees Fahrenheit, degrees Rankine, degrees Celsius, and Kelvin? Okay, so currently you have 110 Fahrenheit and 68 degrees Fahrenheit. So the difference in Fahrenheit, obviously, you just subtract it and you're going to get 42 degrees Fahrenheit. So now we have to change that into Celsius. So how would you do that? 42 minus 32. It's going to be 1050 over 9. So that's what? 5.55 all the way. 5.55 repeating. Is that 5.55? Is that where we at? Where are we at? In Fahrenheit. Okay, C. Okay, what are we doing here? Okay, I got that. A was good. B, do that in Rankine. So Rankine is what? It's the same thing, right? It's Rankine is the same thing because, okay, let's do this Rankine first. So this is A. And B, as we do the Rankine, is the same because this is, you're going to change this into Rankine. You're going to do this plus 459 minus, you're going to change that. You're going to add the 459 also. So those two cancel out. Same thing, you're going to get 42 degrees Fahrenheit, right? Okay. So let's go ahead and now do the, was C the Celsius? Celsius. So let's go ahead and do this into Celsius. So it's going to be minus 32.5/9. Minus, change this into, it's going to look like that. Okay, so what are we going to end up getting? We're going to end up getting, this is going to be, so this guy here, the end ones cancel out, right? I'm just going to go ahead and do it. 559 minus 169 minus 349 plus. So this is what I mean. These two cancel out. So you're going to end up with 210/9, which is 70/3, 23.3. So it's going to be 23.3. And so the difference in Kelvin is also going to be the same thing, right? It's going to be 23.3, right? It's going to be the same thing, right? Okay. So that's that. What else do they want? Is a 1 degree temperature difference in Celsius equal to 1 degree temperature in Kelvin? The answer would be yes. Is a 1 degree temperature difference in Fahrenheit equal to 1 degree temperature in Rankine? The answer would be yes again. They're the same thing. We just proved that. Okay? All right. That's that. So I'm going to give you some homework on that. I also went ahead and created the homework assignment for the notes, so you can go ahead and upload your notes on Google Classroom.